All right, lesson 5 for chapter 4, friction, a closer look, right? So remember, this is very important right here. Many times people don't realize friction is a serious thing. Um, I always like to think of friction, okay, as fun, right? Friction, F, U, and then the normal force, okay? A lot of people realize that normal force is not always equal to mg, and that's a good thing, okay? Okay? Because depending on what other vertical forces are acting on the object, it could be more than mg or it could be less than mg. And that is very, very important, okay? So I would definitely memorize this, okay? Now, if F normal, okay, is bigger than mg, right? If additional forces, right, are pushing down on it, okay? Okay? And F normal is less than mg, okay, if, right, additional forces are pulling up on it, okay? Okay, so your normal force does not always have to equal to mg, which is the weight of the object. Now, if there are no other vertical forces, then it can equal to mg. So this is very, 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 very important, okay? So don't ever think F normal is always equal to mg, okay? But what happens when frictional force is bigger than the applied force? So we can calculate the frictional force using mu times F normal, but this calculated force value doesn't always have to be that value all the time. And here's an example of that. So what happens when the frictional force is bigger than the applied force? So let's say there's a friction between the block and the table here, and you're only pulling with 35 newtons of force in the positive x direction. Here, since there are no other vertical forces acting on it, we will have Fg going down and F normal going up. All right, so let's draw those force diagrams. So here's my Fg, which is equal to m times g. And then there's going to be a normal force from the table to the object, and that's my F normal. So in this particular case, because there are no other vertical forces other than mg, F normal is equal to mg. And we can easily prove that if we were to take a look at sum of all forces is equal to ma in the y direction, okay? And then sum of all forces in the y direction, there are two forces, right? That's F normal plus, right, Fg, right? And since there's no acceleration in the a direction, right? So ma is equal to F normal. I'm going to consider up direction positive, right? I'm going to consider up direction positive. So my F normal is positive, and my Fg then becomes negative. And since acceleration in the y direction is equal to 0, 0 is equal to F normal minus Fg, right? Therefore, my F normal in this case is equal to my Fg. Okay? So to calculate my frictional force, right, since they gave us the mu, both mu static and mu kinetic happen to be the same thing of 0.7, right, we can calculate the normal force. So F normal is equal to Fg, right, which is equal to m times g, therefore 6 times 9.8. So what is that, John? Okay, so 6 times 9.8, and I get 58.8, right, newtons. So that is equal to 58.8 newtons for my F normal and for my Fg. Therefore, when I calculate my friction is equal to mu times F normal. Well, my friction then is equal to 0.7 times the normal force of 58.8. Okay, so what is my friction? My friction comes out to 41.16 newtons. Right? That's my frictional value that is calculated. That is the maximum. Right? This is the maximum amount of friction the system can possess. Okay? So, if I were to pull on this thing with 35 newtons of force, okay? So, if I am pulling this thing, I guess, you know what? Let's use purple for this. So, F pull, let's say, happens to be 35 newtons of force. Right? Then my Fg, right? My Fg is this way. Right? My Fg. And my F normal is this way. And my frictional force is going to hinder from motion, or it's going to basically resist in the direction of motion. So here's my F friction. Now, does that necessarily mean this friction has to be 41.16 newtons? If that's true, then this frictional value is going to be bigger than my F pull. That means my friction is going to make this thing accelerate that way. That doesn't make any sense, right? If this frictional value can have maximum value of 41.16 newtons, right, it would react to whatever pull that this thing experiences, okay? So, to state my point, here's my calculator. Let's say this calculator has frictional force maximum of 41.16 newtons. If I were to apply a force of 35 newtons, will it move? And the answer is no, it won't, because that's not enough to budge this thing, because this thing can possess maximum of 41.16 newtons. Okay? So there's no acceleration happening for the system. Okay? So the acceleration really is equal to 0. And we already know the acceleration in y is also equal to 0, right? So it's not going to accelerate, okay? So if we were to use F equals ma to calculate the acceleration, right, you know the acceleration has to be 0, okay? So sum of all forces is equal to ma, and this time let's take a look at the x direction, because we already know what happened with the y direction. Then sum of all forces, right, is equal to, in the x direction, right, I have force pull plus friction. So max is equal to, I'm going to consider this direction positive because that is the direction of motion or its intended motion. Therefore, F pull becomes positive and my friction becomes negative. We already established the acceleration in the x direction has to be 0 because this does not have enough force to push this thing and break this thing, right? Therefore, since my acceleration is 0, this whole thing goes to 0, right? So that is equal to my F pull minus F friction. So even though my frictional value can be calculated to be 41.16 newtons, in this particular case, my F pull is equal to my friction, or should I say, if I bring this friction to the other side, right, my friction is equal to my F pull, right? So since F pull is equal to 35 newtons, right, my frictional value is also equal to only 35 newtons. Now, it came out to be positive here. That's because we already gave the direction of friction to be negative. So if we put this in this frictional variable, it becomes negative 35 newtons. So it is correct that it's pointing in the negative direction. So my friction does not have to be more than this in order to react from this pull. Okay? So my frictional value comes out to 35 newtons. So here is the answer for number 3. All right. So what happens if I were to pull this thing with 40 newtons of force? What's my frictional value? It has to be 40 newtons. Now, if I'm pulling this thing with 41.16 newtons, right, at that moment, this thing's going to start to budge. And my frictional value is going to be 41.16 newtons. Now, if I were to pull this thing with 50 newtons of force, right, then my frictional value will be just 41.16 newtons because that's the maximum value this friction can possess. All right? So if I were to pull this thing with 51.16 newtons, my frictional value will be still 41.16, but my net force in the x direction will no longer be 0, but it will be 10 newtons. Okay? All right, so that's very important concept for friction. All right. Any questions? All right. All right. So, let me see. All right. Good. All right. Then let's move on. All right. So Justin, I got in. Liam. Okay. So here's an example problem. Friction and the normal force. A woman pulls a loaded sled of mass 75 kilograms along a horizontal surface at a constant velocity. And this is like a main line problem. Like you only see like this thing happening in main line where a woman wearing a Gucci jogging suit pulling on a sled with 2 pumpkins along the street of Lancaster, right? So there's lots going on here, right? A woman pulls a loaded sled. So this whole mass here happens to be 75 kilograms along a horizontal surface. And here's the key word right here. At a constant velocity in the horizontal direction. That tells us the acceleration in the x direction is equal to 0 because it's moving at a constant velocity. Okay, and that's very, very, very important. Okay, the coefficient of kinetic friction, mu sub k, between the runner and the snow happens to be 0.1, so this is equal to mu sub k. And the angle phi here happens to be 42 degrees. They're looking for the tension, right, in the rope. I guess if you want to, you could say F tension. Because this capital T also means time, period. Okay. Let's do that, okay? So they're looking for the tension in the rope. So how much tension is there to make this 75 kilogram mass move horizontally at constant velocity? So let's assume this object right here, right? Let's assume this object as a point particle. So let's draw a free body diagram. Boom, right there. That's the mass of 75 kilograms, okay? And let's do a free body diagram on this, John, okay? So here I have tension, so here I have F tension, and I have Fg, and I have F normal. Now, again, these are not to scale. And I have friction. Fg has to be a lot bigger than this, actually, if you want to make it into a scale. So okay. And here's the reason why. This F tension will have horizontal and vertical component of the F tension. So this angle here happens to be 42 degrees. And this is F tension Y. And this right here is F tension X. So let's calculate what these F tension X and F tension Y are so we can actually have everything on the axis of X and Y, right? Because this is sort of like in the XY plane. So F tension Y is equal to F tension, since this is the opposite sine of phi, right? So F tension y happens to be F tension times sine of 42 degrees. So what is that? Sine of 42. Well, let's take a look. Sine of 42 degrees comes out to 0.669. Okay, so this is equal to 0.669 F tension. Okay, so this F tension is this, if this F tension is this F tension right here. Okay, so this can be, I guess, that darker navy blue. Okay. Similarly, F tension X is equal to F tension, right? F tension times cosine of phi, and that is equal to F tension times cosine of 42 degrees, and that is, right, so cosine of 42 comes out to 0.743 times the F tension. All right? So now that we have all this, if we were to like sort of redraw this without using this F tension, right, we would have F normal, FTY, FG, F tension X, and friction. Okay? So let's think about all the forces that are happening, okay, vertically. Okay? Let's take a look at Y direction. So sum of all forces in Y is equal to MAY. Now, you know this sled and pumpkins are not going to accelerate upwards, or it's not going to accelerate downwards, so the acceleration in Y has to be 0. Okay, that can be safely assumed. Then sum of all forces in Y is equal to, okay, I have 3 forces in the Y direction. I have this force, I have this force, and I have this force. Okay, so I have F normal plus, right, F ty plus Fg. Okay, so if I set these two equal to each other, MAY is equal to, right, F normal. I'm going to consider going up direction positive. That means going down will be negative, so F normal is positive. Then my FTY is also positive because it's pointing up. However, my FG is pointing down, and that is negative. We already established that AY is 0, so this whole term just goes to 0. So 0 is equal to F normal, which we don't know what that is yet, right? Plus FTY is 0.669 times FT. Minus mg. So what is this mg? Well, mg is equal to, right, 75 times 9.8. That is my Fg, right? So what is my m times g. I get 735 newtons. That's my Fg. So now if I solve for F normal, I'm going to bring this to the other side and it becomes positive. I'm going to bring this to the other side, that becomes negative. So F normal now is equal to, right, mg, this is going to be positive now because when I bring it to the other side, is 735, right, minus, if I bring this to the other side of the equal sign, it's going to be negative, so minus 0.669 F tension. So I have one equation here with two unknowns. Ultimately, we're looking for this. Okay. So now let's take a look at the x direction. Okay. Sum of all forces in the x direction is equal to max. And we have already established that ax is equal to 0. Right here, right? So, sum of all forces in the x direction, there are two forces in the x direction. We have Ftx and we have friction. So I'm going to consider the direction of motion to be positive, which is positive x-axis to be positive. Then, right, Ftx plus friction is what we have. So when I set these equal to each other, right, max is equal to Ftx positive. F friction, since going in the opposite direction, is negative. We know ax is 0. We already established that. So ax is 0. We also said Ftx is 0.743 F tension, right? Minus mu times F normal. This is F normal, and that has to be substituted in here. All right? So, I'm going to bring this down here, and then substitute that in there, and we're going to have a larger mess. Okay, so here we go. So 0 is equal to 0.743 F tension minus, right? I should make it red. Minus mu times, right, this whole mess, right? Mu times 735 minus 0.669 F tension. We already know that this is 0.1, right? So this is already 0.10. That's mu. So if we were to distribute this through, so 0 is equal to then, right, 0.743 times F tension. If I multiply this times this, I get negative 0.1 times 735 is negative 73.5. And if I multiply negative 0.1 times negative 0.669, I get positive, right? Positive 0.0669 F tension. So if I bring this to the other side of the equal sign, it becomes positive is now equal to, if I add these two terms together, right? So it becomes 0.8 something, right? So I get 0.743 plus 0.0669, and I get 0.8099 F tension. All right. So let's solve for F tension. So my F tension is equal to simply 73.5, divide that by 0.8099. So what is that? Okay. So 73.5 divided by answer, I get 90.75 newtons as my F tension. All right. So I know it looks intimidating at first when you look at the whole thing at one shot, but if you were to follow exactly how I did it, step by step by step by step, it should not be as intimidating. Okay. It's always a nice idea to draw the free body diagram, even though it doesn't say it. Most likely I will probably mention it, okay? And figuring out all these components first, then split them up into x and y directions, right? And then work it out individually, okay, in the x directions and y directions independently from one another, right? I chose to do the y direction first because I needed F normal to figure out F friction, right? It wouldn't matter because here you would have still ended up with two unknowns anyway. Then you would still have to figure out the F normal. Then you'll realize that you have to use the y direction to figure out the F normal. So whether you started with the x direction or the y direction shouldn't matter, okay? So once you have the two equations with two unknowns, okay, you can substitute one into the other to figure out just one single variable, and voila, there you have it. All right, any questions? All right, good, good. Next, we're going to be talking about something on the inclined plane, okay? When we have something in the inclined plane, okay, first rotate your axis so that this x-axis, otherwise x prime, right, is going to be parallel with the incline, and your y-axis, or y prime, which once is rotated, is perpendicular to my incline, okay? So you could say that this is like your x prime. That's not a derivative. It's just another form of x, new x, right? And this would be new y, you know, y prime. So it's not a derivative here. It's just, all right? So once you rotate the coordinate system, you work it as though it is this. So find all the components in your x prime, y prime axis, okay? So when this object is on an incline like this, your FG will always be pointing straight down, okay? And because your FG is always pointing straight down, it will no longer be on the X or Y axis. It will be on the X prime, Y prime plane. Okay? And of course, this is always equal to mg. Then, this FG can be broken up into its X and Y prime components. So here, this will be my FGY prime, and this would be my FG X prime. This angle right here between FGY and FGX, this angle is 90 degrees. But what is this angle right here? Well, if I were to look at this on separate on separate triangle, let's see if we could derive this together. All right. So here I have this, right? And if I were to bring this FG straight down, right? And this right here is your FGY prime, right? Which is perpendicular. Since this angle here is complementary angle, I'm going to call that angle alpha. Since alpha is complementary angle of my angle theta here, this is 90 degrees because it is perpendicular to my incline. So this angle has to add up to 90. And since theta plus alpha has to equal to 90, this angle is also complementary to, right, alpha. So this angle has to be theta. There's no negotiation on this. All right? So we just proved that this angle, the small triangle angle, and this angle has to be congruent. Now that we proved it, you don't have to keep proving it, you just use it. All right? So this theta are equal to each other. Okay? That means your FGY, right? So your FGY sometimes is known as F perpendicular because it is perpendicular to my XY plane, right? Well, I mean my X prime axis. So this is equal to simply FG times, this is adjacent to my angle theta, so this has to be cosine. And FG X prime is equal to, this is my hypotenuse FG, right? Times, since this is the opposite of my angle theta, it is my sine of theta. These two thetas are same thetas, okay? So one thing, this FGX prime will always point down the incline, okay? Whether this object is standing still, sliding down, or sliding up, it doesn't matter, right? Why? Because gravity will not change its direction, whether this thing is sliding up, sliding down, or standing still. So my FGX will always point down the incline no matter what. Okay? Similarly, my FGY prime will always point perpendicular to my incline downwards. So when I add these two components, it should equal to my FG. Okay. Sometimes people make a mistake of like flipping this arrow that way because it's sliding up. That means it's going to go faster and faster up that way. It'll never come back. The reason why this is pointing down is because of gravity. And gravity will not change its direction. Okay? Then, once you have all these things, then you can solve. Okay, so here, this is my F normal. My F normal and my FGY are pointing in the opposite direction of one another. Okay? So, if this were at rest, so I'm holding it down like this. So I'm holding it down like this on an incline, and then I let go. What's going to happen to this? Most likely it's going to slide down, right? And it's going to accelerate down. But it's not going to be accelerating at the same rate of 9.8 because it's on an incline. Okay? Because if I were to lower this to a very shallow angle, it's not going to go like that. It's going to go very slowly at first, and then it's going to slowly accelerate to higher velocity. Right? Similarly, if I go to the other side, and if the incline's like this steep, and if I let it go, it's going to go, right? But not 9.8 meters per second squared. It'd be less than that. If I had friction acting on this, and I release this thing, my friction will act up the incline because it will always go opposite of motion, right? So if the friction is acting this way and my FG is acting that way, hopefully my FG is bigger than my F friction in order for this to slide down. If my friction is calculated to be bigger than my FG, then it will not slide down. It will actually stay, but my frictional value has to be exactly the same as my FGX, even though it can be calculated to be greater than this FGX. Okay? If this thing were to slide up, let's say you like flick this thing and it goes, starts to slide up, your FGX will still point downwards, but this time your friction will also point downwards because it's opposing the direction of motion. So no matter what, this will always point down. But the direction of friction can change depending on what this thing is doing. If it's sliding down, friction's pointing up. If it's standing still, friction's pointing up. If it's sliding up, your friction is pointing down. Okay? It's very important that you understand that. All right. Then identify all the other forces. So let's draw this thing here when it is at rest, sliding down, and sliding up. So we could have three different things to understand. Okay? So here, let's say standing still. Let's do that first. Okay, so this is at rest. Okay, so if I were to do a free body diagram, do I need to draw all this? I'm gonna just draw point particle for this box. Okay, so here's the box. Your FG will point straight down. Your F normal will point perpendicular. Right? So here's your F normal. Here's your FGY prime. And here's your, I drew that a little too long, sorry. Here's your, so this should be here, but it's too long. Okay. This is your FG X prime. Once you draw these two, you don't need your FG anymore because you splitted this up into its two components. So don't put this in some equation unless you're going to be finding these two. Okay. And since it is standing still, my frictional value has to be in the opposite direction of motion or its intended motion. And this friction is along the incline, parallel to the incline, same value as my FGX. Okay? So standing still, my friction is equal to my FGX. In this particular case, it could also work for or sliding down at constant velocity. So this can work for standing still or sliding down at constant velocity. Okay? So the next one is going to be sliding down, accelerating, okay? For sliding down, accelerating, here again is your mass, and this will go down as your FG. And then you have F normal going this way. Oh, crap, wrong color. So here's your F normal. Right? And then here is your FG Y prime. Right? And here's your FG X prime. And your frictional force is definitely smaller than your FGX. Okay? So when it's sliding down, accelerating, your FGX prime is definitely greater than your F friction. Okay? Now, let's think about sliding up. sliding up, before I even write down this part, I want to do this first. Sliding up, it's not going to be accelerating, but it'll be slowing down. It'll be decelerating, sliding up. And I'll show you why. Because here's my FG. Here is my F normal. And here is my FG y prime. And here's my FGX prime. And since it's sliding up this way, right, my friction has to act down the incline. Okay? So here, my friction is acting in the same direction as my FGX. So when this thing is sliding up, it is actually slowing down. Okay? And if you were to make the direction of motion to be positive, this will have your FGX prime, right, is going to be positive, and your friction will be negative. Okay? Here, your FGX prime is positive, and your friction here is negative. Here, your FGX prime is negative, and your F friction is also negative. So you could say that this direction here is positive, and you can say this direction here is positive, and this direction here is positive. All right. And we don't know if the friction is going to be bigger or smaller than FGX. We just don't know that. All right. It could be bigger, it could be smaller, it could equal to each other. So we don't really know. Okay. Hopefully that should help out. Okay. It's very important that we understand this. All right. Okay. So once we identify all this, depending on the situation, then we can apply sum of all forces in the x direction is equal to ma, and then sum of all forces in the y is equal to ma. Now, most likely in the y direction, it's going to be 0. Here, it depends whether its friction is bigger or smaller, right? This acceleration can be 0, it could be positive, or it can be negative, depending on the situation. Here, acceleration 0. Here, your acceleration is positive, down, right? Here, your acceleration is negative. Maybe we can write that down here too. The acceleration here is 0. Here, your acceleration is positive. Okay. And here, your acceleration is negative. Okay. Now let's take a look at an example problem that deals with this inclined plane. All right. So here, a skier, right? A skier has just begun descending the 30-degree slope, assuming the coefficient of kinetic friction is 0.01. Must be skiing in Poconos because that's a really low coefficient of friction. It's probably very icy, right? And Poconos is very icy, so you want to go up to like Vermont. First, let's calculate the acceleration of the skier, right? B, the speed of the skier after 6 seconds, okay? So, well, first of all, they don't even give us the mass of the skier. So we don't even know if the skier has mass of 25 kilograms like a little kid, or maybe 50 kilograms like an average human adult, or maybe it could be like 95 kilograms, right? Like a huge athlete. We don't know, right? The mass of the skier, we're just going to keep it as M. However, we do know the skier will have weight because it cannot escape gravity. So the skier will have Fg, which is equal to M times G. And we can break this skier's Fg into its components of, right, Fg y prime and Fg x prime. This angle here is same angle as that, and that is 30 degrees. And this here is a right angle, 90 degrees. And this skier will also have normal force going perpendicular to the incline. So that's my F normal. And the skier will also have friction. And the friction, since the skier is going down this way, that's the direction of motion, right? This is the direction of motion, and that is the positive direction. And my skier will have friction going up this way, opposite direction of motion. All right? So that's good to know. Now let's take a look at what's going on with x direction and y direction. Okay? So this time I'm going to start with x direction first, just to be different. Okay? So let's take a look at the x direction, just to show you that it doesn't really matter which direction you start with first. So in x direction, or should I say x prime direction, right? I have sum of all forces is equal to m a x. And sum of all forces in the x direction, I have two forces. I have F g x prime plus friction. So MAX, if I set them equal to each other, is equal to, right, FGX, and that is positive because that is going to be going in the direction of motion. So my FGX minus friction. Now my FGX is equal to, right, FG times sine of theta. Remember that? And that is same as, that is also equal to m times g times sine of 30 degrees. Because we don't know what the m is. I mean, we know what g is, we know what theta is, but we don't know what m is, so we're going to leave it as m. So ma x is equal to, here is mg times sine of 30 degrees. Just leave it as that, 30 degrees. Minus friction is mu times the F normal. We don't know what F normal is. We don't know what F normal is. So we have one equation here. We have one equation here, and we have no idea what AX is. We don't know what mass is. We know mu. F normal, we don't know. I mean, if you want to take one more step, right, and plug this as a 0.5, and this, we already know it as 0.01, we can do that if you want, okay? So you can say MAX is equal to, right, M times G, and sine of 30 is 0.5, so 0.5 times M times G, right, minus 0.01 times F normal. So that's what we have. Now let's take a look at the y direction. Sum of all forces in the y direction is equal to MAY. I mean, unless this skier is going to have a yard sale, like losing all the poles and gloves and skis flying everywhere and accelerating off the slope, or going into the slope, right, face plant, right, the acceleration in the y direction is going to be 0, right, assuming that skier is going to stay on the slope. Okay, so sum of all forces in the y direction, I only see two forces, and that is my F normal plus, right, FGY prime. So these two forces are the only forces in the y prime direction. Okay? I guess I could put the x primes here. Right. And if I were to say MAY now is equal to then F normal, I could keep that positive, right? And FGY, right? I could keep that negative, right? FGY prime. And we said that this is 0 unless the skier is having a yard sale. Right? So F normal minus FGY prime is, right, FGY prime is equal to mg cosine theta, right? So mg times cosine theta. So if I solve for F normal now, by bringing this to the other side, my F normal then it is equal to positive m times g times cosine of 30 degrees. Well, Cosine of 30 is 0.866. So 0.866 times mg is what we have for F normal then. Well, I can actually substitute this into here. Then I would have MAX is equal to, right, 0.5 mg minus 0.01 times 0.86 times mg. So that's my F normal right there, right? So if I distribute this thing through, I have MAX is equal to 0.5 mg minus, right, 0.00866 mg. Okay? All right, so if I add these two, right? So it's 0.5 minus that, really, right? So my MAX is equal to 0.49134 mg. Guess what? It doesn't matter what the mass of the skier is because my masses can cancel out to 1. So my acceleration in the x direction is equal to 0.49134 times 9.8. All right, so my acceleration in the x direction comes out to 4.8, right? 82 meters per second squared. Wow. That acceleration is pretty significant, actually. So that was part A. What about part B? Well, for part B, we know the skier is accelerating at this, right? So I'm going to do part B up here. So we know the acceleration of the skier is 4.82 meters per second squared. We know just begun, so initial velocity is 0. Okay? And the time that we have is equal to 6 seconds. They want to know how fast the skier is going after 6 seconds. This looks like equation number 1, right? Vf is equal to Vi plus At. So Vf is equal to initial velocity, 0, plus 4.82 times 6. So my final speed after 6 seconds of going down, right, bombing the slope, is equal to 28.89 meters per second. That doesn't seem fast. However, if we were to convert this 28.89 meters per second into miles per hour, right? We first multiply, right? 3,600 seconds, 1 hour. And there are 1,610 meters in 1 mile. All right? So let's see what happens. So multiply that by 3,600 and then divide that by 1610. That is 64.6 miles per hour. So if you crash, that's like falling out of a car doing 65 miles per hour, right? And that's very bad. That's why when you ski, right, you should not be going straight down with your, skis parallel, and you should really ski in control, right? Like, when you start skiing, say pizza wedge, right? And French fries, pizza wedge, right? Well, my boys are Asian, so I say chopsticks, right? And pizza wedge, right? They understand that much more. Anyway, hope you enjoyed this problem. So, I'm going to give you the rest of the period to take a look at these homework problems, which you should be working on today and tomorrow. And we will have class probably on Thursday, even if it snows. Other places all cancel, but since we are actually having, virtual, we could definitely have it. So the rest are all pretty much problems, and you're going to have to do all these problems eventually. So there's a lot of problems here. So you're going to have to do all these problems, okay? And I'm going to actually give you an assessment over the weekend to cover up to this. All right, so get to work on this, and I guess we have 5 minutes left still. All right, so let me see. Oh, I got 2 minutes. Yeah, I guess you're not going to have enough time to start this thing. All right, I'm going to end it here then. All right, I'll stop here.